second one. We have this one. Okay. With a metal here. And what we are doing is basically we are doing a sulfurization. Again, what we have to look is where is the orientation of this oxygen heterocycle. Again, because it's a 5-member ring, the orientation will be C2, only because it's a furan. It's the basic orientation of the furan. And then we have a metal in this position. Metal is electron donating group, as before. By induction means that the orientation is orthopara. Ortho, ortho, meta. They are no para position because, remember, we cannot go through the oxygen, always only through the carbonate chain. That means that if it's orientating ortho, we will have an activation in this position and in this position. Again, in this position is activated by the furan. In this position is activated by the metal. But this position is activated by both. That means that the reaction will take place in this position. Obtaining this compound. Okay, next one. We have this compound. This pyridine, and we add methyl iodide. What we have to take care now. Pyridine is electron poor ring. Okay, it's a 6-member ring. We have a nitrogen. That means that nitrogen takes more than one electron. It's more electronegative than the carbon. That means it's taking more than one electron. At the end of the history, the nitrogen is an electron poor ring. If it's electron poor, we will not be very motivated to do electrophilic aromatic substitution. But this nitrogen has a pair of electrons, isn't it? These pair of electrons are not part of the p system, are available. This is why the pyridine is a base. But this can act as a normal pair of electrons. We do the SN2, and what we have is the formation of the pyridinium cation. Okay? That's all. Okay. Next one, we have a pyridine. And we add we have a pyridine with a chloride in the para position, we have a pyridine with a fluoride in a para position. We attack both compounds with the same nucleophile, that means dimethylamine. And the question is, which will be faster, the chloride or the fluoride? Okay, in order to answer any question about how fast is a reaction, we have to check which is the rate determining step. This basically is a nucleophilic aromatic substitution. The rate determining step will be the first step, the addition of the nucleophile to the pyridine. I will put a general one, okay? X can be chloride or fluoride, and we form this internally, okay? That means this is the transition state. This is the rate determining step. Which will be faster? Okay. There are two things that make this reaction faster. First is how electronegative is this atom, the halogen atom. Okay, when more electronegative will be, more a density positive charge will have this carbon, and more attracted will be the nucleophile. That means chloride and fluoride. Fluoride is by far, fluor is by far more electronegative. That means that this position will be by far more electropositive. Will have a density, a bigger density positive charge. Second thing, in order that this nucleophile approach to the aromatic ring, how difficult it is. That means how big is this atom? When bigger is this atom, more difficult will be. And again, fluoride or fluor is smaller than not chloride. It's from the second line, the second row. Fluoride is from the third row. That means that this is smaller. That means everything indicates that this will be faster. Okay? A common mistake is to say that this will be faster because the fluoride is a better leaving group. That's not true. Okay? Formally, it's not true. We have to analyze the rate determining step and then check which characteristics of the atoms are making the reaction faster or slower. Okay, we have here imidazole and we add okay, remember which is the most active position of the imidazole is this position, the C2 position. That means that the bromination will take place in this position. One, we are doing exactly the same but with imidazole, the same that we did before. We are adding formaldehyde, dimethylamine. What is happening? Basically that when we are adding formaldehyde with dimethylamine, what we will form will be the iminium, okay? And then this will attack. Remember, indoles are very good nucleophiles. That means that we attack the iminium, which is the favorite position in the case of indoles, C3 position. This position will be favorite. Remember why? Because it's the one that has more resonant forms that are valid. Okay. And we have this final compound. Okay, next one, we have this compound. We add butyllithium and acetic anhydride. Well, butyllithium is a strong base. What we need to decide is which is the most acidic proton, and the most acidic proton will be the one that is attached to the heteroaromatic, to the heteroatom ring, to the nitrogen. We will form the anion here, and then the anion will attack the anhydride, getting this compound. Okay? Next, we add butyllithium. What will happen? We add ethyl iodide. Okay, basically we have to analyze which will be the most acidic proton. We will remove this proton here, and what we will get is the anion here will attack the ethyl to form this compound. we do just the opposite, synthetic steps, that means first sorry, this was wrong. Okay. Instead of oxygen has to be a nitrogen, if not also it's not working well the aromaticity. There are a mistake in the exercise. Okay? If we're doing the exactly opposite, we add butyllithium. Butyllithium will remove the hydrogen more acidic, that is the hydrogen is bonded to the nitrogen. We will generate an ion here, and this anion will attack the ethyl iodide to form this compound. Next, we add butyllithium, acetic anhydride, and what we will do is to deprotonate this position because it's the most acidic position. Okay, and we will form an ion here that will attack the acetic anhydride to generate this final compound. Okay? Be careful because in the exercise that I have, here is an oxygen and cannot be, has to be a nitrogen. Okay? Okay, go for the next one. We have this compound. And we add bromine. What could happen? Well, basically we have here, probably we need to add iron chloromazine already that works as a catalyst. Okay, we have this reaction. This is basically electrophilic bromination. Electrophilic aromatic substitution, and we have to decide in which ring will take the place the reaction. Okay, here we have a benzene with an electronegative group, and here we have a 5-member ring with an electron withdrawing group 2. Then, which is more active in the electrophilic aromatic substitution? A benzene ring or a 5-member ring? A 5 heteroaromatic ring? Always will be the 5 heteroaromatic ring. This will be more active. And basically, we don't have to care much about which position, because the only position available is here. That means that what we will have is the bromination in the free position of the 5-member ring. Okay? Right? Okay. Then we have this compound. Okay. We add butyllithium and ethyl iodide. What will happen is that, as before, we have to choose. This is a strong base. We have to choose which hydrogen is more acidic. Obviously, the more acidic hydrogen will be the hydrogen that is bonded to the nitrogen. And basically, we will form an ion here and will attack the ethyl. Then we attack again with a butyllithium. And now which will be the most acidic proton? The most acidic proton will be here. This hydrogen will be the most acidic proton. That means that we will deprotonate this proton. We will generate a negative charge here. Okay? And then this will attack the acetic anhydride, and what we will get is the this compound. Okay? Next one. We have this compound. We add butyllithium. Again, what we have is to take care which is the most acidic proton. That will be again the one that is bonded to the heteroatom. We deprotonate here, we form an ion, and then the ion will attack the acetic anhydride to form this compound. Okay? One, we have this, we add butyllithium again, ethyl iodide. We will remove the most acidic proton, that is the proton in the middle position. We will form an ion here and we'll attack the ethyl in order to form this final compound. Okay? Check always that when we are adding a strong base, we have to decide which is the more acidic proton in our starting molecule. Okay, we go for the next question that basically is propose a synthesis for the following compounds using the starting materials that are written. First one is this compound from this ketoester, right? Well, how we can do it? Basically, we can start with the ketoester. This is a pyrrole, okay, with a 5-member ring. That means that we start with this ketoester, and the first thing that we will do is to add a nitrogen in this position. How we can do it? Basically, we can use this in acid media, okay? Sodium nitrite in acid media, we will generate the oxime. With this oxime, the only that we need to do is zinc in acetic acid, and we reduce to form the amine. Okay? This amine is then reacting with another molecule of the ketoester, and what we do is this amine is forming the imine, okay? And then basically tautomerization imine enamine. We will form the enamine here. Basically it's the only option that we have, but remember, if we have two options, always we will form the enamine in the most acidic proton, with the most acidic proton that always will be the one that is in the middle of the two, of the carbonyl and this imine. We'll have this. And now this position is nucleophile, that means that this will attack an electrophile. Remember that the position, the carbonyl position is electrophile, that means that we will have intramolecular aldol reaction. Okay, we generate this 5-member ring, and then simply we protonate this oxygen. Okay, we protonate again this position in order to make a good leaving group. Simply we can cancel this hydrogen from here to here. And what we will get is okay. Now this is a very good leaving group, it's water. I will remove this. Okay, it's water. Water is living. What we form is a carbocation. Simply elimination. We form the double bond here. And then simply tautomerization imine enamine to form the final compound. Okay? Good. Then we go for the next one. We are trying to form this one. Okay, from this one. Okay, basically what we are doing is the formation of five-member ring. Remember that for the formation of five-member ring, one possible option when we have substituents in these positions, in the positions C2, is that this is coming from a 1,4 carbonyl compound, and the 1,4 carbonyl compound normally is coming from Umpolung addition to a Michael